in a second. Okay, right. So what we're going to do today, guys, we've got the last little bit of the content. Again, if you guys have any issues hearing me, let me know as well if you've got any issues on that front. Just going to check. Yep, that's good. Right, okay, cool. So today what we're going to do, guys, is we're going to have a look at the last bit of the content, which basically looks at what we class as fluid flow. Okay, so fluid flow is a really simple part actually of the last bit of the unit. What you'll also be pleased to know is there's no maths involved today. So it's basically understanding some key principles and then applying them to given situations. So just making sure you can understand that. So hopefully you guys can see this Jamboard. I can share this Jamboard with you as we go as well, if you'd like. Okay, so no maths today, you'll be pleased to know. So what we are going to do is we're going to start to talk about what we mean by fluid flow. This is going to bring us into these ideas around something called streamline and turbulent flow. You might have heard of these words before, so if any of you have been on a plane before, you might have heard of the word turbulence. And it's kind of where you get a bumpy ride. Okay, so we're going to think about what turbulence actually means. We're going to relate essentially flow of fluid to these two key words. We're then going to begin to think about, you know, what do we actually mean by streamlines, and we're going to compare the two kind of different types of flow. Now, what I wanted to do to start with is just think about this. What is a fluid? So just guys, start to think about what do we actually mean by fluid. Type into the comments box, turn on your microphone and shout out if you prefer. Really up to you. What is a fluid? Any ideas at all? I'll give you a bit of thinking time there. So some of you are probably typing away frantically. So Stephen says a liquid. Okay, so we could possibly accept that as a starting point. Okay, so we're putting a question mark in front of that. Is it a liquid or a gas? Okay, so Theo says a gas. Is it a gas? Okay, that's fine. You're not right, but you're not wrong. Okay, so it's kind of, you're kind of there, but it doesn't completely answer what we mean by a fluid. Bonds are separated. So you mean the molecules themselves are not interconnected? Perhaps is what you mean by that, Taylor. Yeah. So okay, so no bonds is possibly what we could think about this. The bonds are key because the bonds allow the molecules to do something. That's the kind of key thing with this. So if we're talking about a fluid, it is about a liquid and a gas. These definitely are fluids, but it's thinking about what liquids and gases can do that solids cannot. Any idea what I'm talking about? What is it that these two things can do? Move around, good. Can fill an area, move. Yeah, okay. So we have essentially these ideas that they can move and they can fill a container, perhaps. So these are good ideas. In physics, a fluid is a substance that continually deforms under applied shear stress or external force. Thank you, Brad. There was a good bit of Google in there, or did that come straight off the top of your head? Who knows? But that's a good idea in that sense. So it's a substance that continually deforms under applied shear. That certainly is something that we can start to think about. Yeah, Google, that's fine. That's fine. You know, we're teaching you to look things up. So let's actually, you know, let's take these ideas and think about what we actually mean by a fluid. That's a really small rubber, but you get the idea. Right, let's just get rid of that bit. I'll rub off the next bit in a minute. Right, so first things first. Let's get rid of this down here. So firstly, a fluid is a substance that has no fixed shape and yields easily to external pressure. That's what Brad's answer was kind of getting at. Okay, so you can mold it, you can make it change shape, you can make it move essentially. That's what we were talking about here with this move idea. That's good. And filling a container. The key thing there as well is it has no fixed shape. Okay, so the next thing that we then note is that it is a gas or a liquid. So you're absolutely right to say it's a gas or a liquid. But it isn't just the fact that it's a gas or a liquid in that sense. It's that kind of idea that it has no fixed shape, and the molecules themselves are free moving in that sense. Okay, so that's really important as well. So let's just delete this last one and see what it says. So a substance that is able to flow. This is really, is plasma a fluid? A plasma would be a fluid, yeah, absolutely. Because it is essentially a very, very hot gas. It's gas that is being given even more temperature or energy, and it starts to emit light. So if you think back to Unit 1, where you guys studied emission spectra, where the electrons jump up a energy level and back, plasma essentially is a gas that is emitting its light as its electrons drop energy levels. But what we should be comfortable with then is when we talk about a fluid is something that is able to flow. It's able to move, it's able to freely fill a container, and it can be easily put under pressure or force to make it move or do something. So that's what we mean by a fluid. That's really important that we understand that kind of concept. Now, fluid flow, I'm hoping these animations seem to be working for me. So you can see these animations are working. Fluids flow in what we call streams. Okay, so a stream, essentially, you can see this going over this car here. You can see 3 streams of air. Now, obviously, we don't generally see air when it flows. But what they're doing here is they're using steam or some kind of gas or some kind of aerosol that's being pushed by wind, and you can see these streams. Okay, so generally speaking, lines are used to show the direction of flow. So what we would do is we draw over the top of this stream, like so. That's the stream. Kind of went a little bit off the piece there, and we'd use a little arrow to show the direction of flow. There we go. So we've got the air flowing over the top, and you use an arrow to show the fluid flow. Okay.
Hi.
Hello.
We're wondering, we're just doing some.
I'm in the middle of a class. Sorry. No problem. Cool. So we can see these streamlines, and we should be comfortable with the idea. You can do the same here. So you've got the water is flowing over this waterfall, and you can see that they're moving, generally speaking, in straight lines. Okay. So lines are used to show the direction of fluid flow. That's key. We've understood that idea, hopefully. And then what we need to be comfortable with is there are 2 types of fluid flow. And these are the 2 types. Now, the first one has 3 different names, depending on, but they're all acceptable. So if you're going to write this in the exam, you can use the word steady, you can use the word smooth, or you can use the word laminar flow. Okay? Laminar flow means that the streamlines are smooth. They're going in a straight line. They do not overlap. And they're nice and kind of, there's order. There's order to this, yeah? Now, the opposite to this is turbulent flow. So turbulent flow is where the streamlines start to mix and they cross, and this is what we call turbulence. Okay, and again, we might have turbulent like in a plane. But the key thing to note there, Brad, is that generally speaking, as a plane flies along, so if you consider if I draw the plane as if it's moving in this direction, so there's an arrow, it's moving into smooth air here. You'll get a nice smooth journey. Now, if a plane flies into this air here, it's going to start to bump up and down, and that's what we mean by turbulence. Okay, so you're absolutely right to relate it to a plane. It's turbulent air that causes that shaking of the plane as it moves through these kind of mixing and crossing streamlines. Okay, so that's the key thing to note. So these are just key words, and you need to learn these, but then you also need to relate them to these diagrams. Does that make sense? So they're quite straightforward, but it's just making notes on this. And again, what I would probably suggest is after this session, flick back through the Jamboard. I'll share the notes and you can go back through and make notes on this. It's also covered on the Google site as well. And I'm recording this so you can watch it back, okay? So that's the difference in terms of fluid flow. What happens when streamlines encounter objects or obstacles? So what I want you guys to do at this point is start to tell me what do you think happens when a streamline comes along and encounters an object. So in this case, it's a football. What things could happen to that streamline? Any ideas? Change direction, brilliant. Okay, so Madison is saying change direction, so we've got that one. So the directional change. That's an R. That looks like that doesn't look like an R. And that's a C, and there's an I in there. Brilliant. What other things? So direction change, brilliant. Bit around object shape, become turbulent. Yeah, these guys, these are good answers. So what you're saying, Dan, is that the streamline in this case will go a bit like that around the object. And then what you're saying, Stephen, is there's a possibility here that you'll get some turbulence and you'll get the crossing of lines like that. Okay, so that's really messy now, but that's the kind of key thing. So what you've got here is you've got lamina here, and then you've got turbulent here. Okay, so that's good. So it becomes turbulent. So it's that movement from lamina to turbulent. And we've gone around the object. So it can't go through the object. The air can't go straight through that object. It's got to go around it. And you can kind of see that here, just where that laminar flow is going around that ball. What else happens then? So we've got a directional change. That's absolutely spot on. What other things can happen to these streamlines when they encounter an obstacle? Shall I put you out of your misery? Friction may occur, yes. What we might call friction is, rather than friction, we'll call it perhaps air resistance. So resistance can occur. I'll just give you guys another couple of minutes to start thinking about what it is before I reveal these answers. Right, okay, so we're going to reveal the answers. So the first thing, obviously, yeah, Madison, you're absolutely right, directional change. We can see that in the red line. The red line goes straight and then it goes around this object. The next thing that can happen is we get velocity change. So what do you think happens to the streamline? Well, it's going to do one of two things. It's going to speed up or it's going to slow down. We're going to explore that further into the session. Okay, so you're not expected to know that just yet in terms of which it does. And then this last one is a pressure change. Okay, now what do we mean by pressure in this particular case? What I want you guys to think about here is isobars. Have you guys heard of isobars? Where do you see isobars? Isobars, you will see these things when you watch the telly and you watch the weather. Okay, so you may have heard of isobars, and they're those lines essentially that they draw to represent the pressure in and around the atmosphere. Now, if they are spaced apart, then that's going to be very different to if those isobars are close together. Now, generally speaking, this is low pressure and this is high pressure, okay? So it's important to note, just in what you might think about is what's happening in here in terms of the pressure compared to the pressure here, okay? So we'll come to this in a minute, okay? So you can kind of think of this in terms of isobars, but we'll relate this then to some actual applications in a second, okay? Right, next job, directional change. Okay, so the first thing to note is when streamlines encounter an object, they will be forced to change direction and go around the object. So you can't go through the object. If this happens, it's possible that laminar flow can transition into turbulent flow. And we can see this here on this airfoil. So an airfoil essentially is a wing of a plane. And you can see you've got this airflow moving across here. And as it goes around the plane, the air becomes more turbulent and it starts to mix and cross. Okay, and that's important that we understand that because we're going to relate back to this airfoil shortly towards the end of the session. And again, we can see here two different wing designs with different points at which the laminar to turbulent transition takes place. Okay, so this line here is called a transition in the sense that we go from the laminar to turbulent flow, and that's caused by a directional change. That's the key thing. Okay, next up, velocity change. So this basically occurs if streamlines are pushed close together. Okay, so if streamlines are pushed close together, the velocity or speed of the fluid will increase. Okay, so this again, it's not, there's no maths involved. All you need to be comfortable with is if you push together these streamlines, they speed up. So the way I've kind of thought you get you guys to think about it is squeezing a hose pipe with water flowing through it. So if you squeeze a hose pipe with water flowing through it, the water will come out at a higher velocity. So think about this here. So we've got low velocity flow here, and it's going to high velocity flow here. Okay, and what we can see is that in this section here, the streamlines are being pushed close together. Now, what we need to think about in here, in terms of this animation up here, is in this region just here, what we can see is that the spacing between these streamlines here and here, and especially here, it's been pushed together. Okay, so what we'll probably find is that in that section in there, the velocity will increase in comparison to here, where the velocity remains, well, there's no change. So the change is 0. Okay, so in that particular section, the velocity change is 0 in that section. It might change slightly because there is a slight bunching as it goes around that object, but it's going to be really noticeable here and here while it goes around that object. I haven't mentioned anything about pressure at the moment, Brad. Okay, so we're only interested in velocity change at this point. So what we're saying is those lines are coming close together, therefore they speed up. So where on this animation can you see the fastest flowing lines is here and here. And actually, if you look really carefully, what I'll do is I'll share this Jamboard with you. You can actually see the speed at which these little dots are moving, and they really speed up at the top and the bottom of this ball. Okay, and where they're really increasing in terms of their speed is any that are kind of going along this line, right the way around that object. They're having to really speed up. Okay, cool. Right, the next one then is pressure change. Now, the key thing to note here is that streamlines move close together, internal fluid pressure decreases. Now, remember what I said. In fact, I think this might be the opposite of what I said. Close together, pressure decrease. Far apart, yeah, it is the opposite, isn't it? Far apart, what is it? No, that's high pressure. So pressure, that is what I said, sorry. So this is low pressure, which is what, again, related to isobars on weather. Close together isobars, low pressure. Far apart, pressure goes up. Okay, so again, think about where we're going to find the lowest pressure on this particular diagram. Yeah, in this particular case, the pressure here drops in there. And in there, the pressure drops there. Okay, so that's the kind of key thing to note in that particular case. What you might find is in this region just here, the pressure will actually increase because of the fact that those streamlines are getting further apart. Okay, and you might find the same here and here. So you'll get a pressure increase behind the object as the air moves over it. Okay, so you can really highlight where these pressure changes are taking place. So what you need to do at this point then is think about, firstly, can you see directional change? Secondly, can you see velocity change? And thirdly, can you see pressure change? And it's just about kind of visualizing this onto the, obviously you're not going to get an animation in the exam, you're going to get a diagram potentially, and it's understanding where these things are happening. So just getting your head around that, make sure that those three factors are taken into account. Okay, so what this then leads us into, so we covered the fluid flow, but fluid flow leads us then into this topic called viscosity. What do we mean by viscosity? Without copying what's already on the board. Okay, so these are our learning objectives. What kind of things come into your mind when we talk about viscosity? type into the comments, turn your microphones on, either way, don't mind. Any ideas? What do we mean by viscosity? There's one thing that really pops into my mind. Yeah, so Guy, you're saying how thick the material is and how quickly it can move. Chloe, you're saying thickness of the fluid. Yeah, thickness is something that comes into my mind. Yeah, definitely. Thickness, and then Guy, you're saying how quickly it can move. So you're relating it then to flow, which is really important. So we've just spent, you know, a bit of time, 20 minutes, talking about fluid flow. So surely fluid flow is going to come into this. Density, again, Stephen, that's good. Density does play a role in viscosity, but it's not always the answer in that sense. So we'll talk about this. So what we're going to do to start with is just talk about what do we mean by viscosity in terms of resistance to flow, understand the factors that can impact upon viscosity, and then begin to be able to recognize differences in viscosity from streamline diagrams. Okay, and then we're going to talk about ways that we can experiment to test viscosity and consider the effect of temperature on this. Some of this you might already be kind of comfortable with, because a lot of it kind of is common sense, but then we need to make sure that we understand the physics behind it. So firstly, we've understood this idea of viscosity. I'm just going to basically stick these into play. Firstly, viscosity is a measure of fluid's resistance to flow. Okay, that's the first thing, and actually it is a quantifiable number. Okay, so we can actually stick a number on the measure of the fluid's resistance to flow. I've used the animation of honey because I think it helps you to understand what we mean by viscosity. Honey it has a high viscosity. It doesn't flow particularly quickly because it is resistant to flow. Okay. It describes the internal friction of a moving fluid. Okay, so this is the friction between the molecules that make up that substance. And is that friction and that resistance within that moving fluid high or low? Okay, and then this last one, a fluid with a larger viscosity resists motion because its molecular makeup gives it a lot of internal friction. So it's understanding the idea. If you were to compare water with honey, which one has a higher internal friction? It's going to be honey. Okay, so water has a low internal friction in that particular sense, and this is what gives honey and kind of, you know, like golden syrup, some oils as well, a much thicker kind of feel. It's all about their viscosity in that sense. Okay, now factors affecting viscosity can be seen in these diagrams here. So firstly, we have this graph here, where we have temperature. Okay, so temperature measured in degrees Celsius, increasing from 0 to 100, and viscosity here measured in millimeters squared per second. So what that's measuring is how quickly, it's essentially a velocity of flow. Okay, so if you pour a lubricant, in this particular case we're using lubricants, so these kind of viscous oils, and you pour them and you measure how quickly they move per second. Okay, and what we can see is, to start with, we can see that the impact of temperature on viscosity. Okay, and then we can also see pressure. Okay, so pressure here has an impact. Again, so pressure measured in psi, and viscosity measured quantifiably again, and we can see that pressure has an impact on viscosity. There's a correlation there. So just making sure you understand these relationships. The other thing to note is molecular structure comes into play. So here we have 4 different molecules in terms of their structure. These might be chemicals, compounds that you've covered with Liz. You certainly have heard of ethanol, and you might have heard of acetone. But what we understand is that these molecules have different viscosities. So again, it's a quantifiable number. So it's just getting your head around the factors that affect viscosity, and make sure you're getting your head around how these 3 factors affect how quickly these molecules flow. Okay, so I'm going to jump past that one, and we're going to move on to the streamline diagrams. Okay, so generally speaking, streamline diagrams for a fluid flowing can be shown again with arrows. So we use the streamlines, and we've got these arrows that go upwards like so. Now, if we have a non-viscous material, A non-viscous substance would be like a gas, for example. So gases have a really low velocity. Viscosity. Sorry, they tend to not be viscous at all. You basically get this streamline, uniform motion. So if you were just following the path of a few particles, like so, they all move at the same rate at the same time. Now, a viscous material is where you get this V-shaped formation. Okay, so think about like goose flying in the air. They fly in a viscous motion. Now, but the key thing to note is at the edges of the flow. So again, if we just follow a couple of molecules on their journey, here at this end, you're getting resistance. That's meant to say resistance. It doesn't at the moment. Let me just finish that off a minute. So resistance. Or you could class this as kind of friction. Okay, so think about it like friction in that sense. And friction slows things down. So what you could actually say is velocity of the molecules here is high, and here the velocity is low, and here the velocity is low. Whereas here, the velocity is the same all the way across that tube. Okay, so that's the key thing to note in terms of the streamline diagram. So we'll get that idea that you've got non-viscous and viscous, and you'll get a kind of combination between the two if you've got very different levels of viscosity. And when we talk about experimental comparison of materials, these animations basically show us what we mean by this. So just have a watch of them again. It's going to flip back and forth. So just watch this one here. What we've got is honey, oil, and water. All of them with different viscosities. And what you'll notice is if you drop a ball into water, it's going to drop faster than it will if you do it into honey and oil. Okay. And all you're doing is you're timing the time it takes to drop a given distance. So basically, you're working out a velocity in that sense. And this experiment here is exactly the same. So you set up 3 measuring cylinders with different liquids inside them, and then you drop a ball into them at the same time. And again, you can see this one's dropped almost immediately. This one's dropping a bit slower, and this one's dropping really slowly. Okay, so if we were to call these A, B, and C, which one has the highest viscosity, A, B, or C? So Stephen's saying C, Brad's saying B. What do we think? Which one has the highest viscosity? So there's consensus now. You're all saying C. Yeah, so viscosity is high. Okay, don't confuse that V there. I should probably put VI rather than V for velocity. So the viscosity here is high, and the viscosity here is low. And you've got if you were to show streamline diagrams for these, essentially you'd have 3 straight lines like that one for that one, and for this one it would be your kind of that kind of straight like that for that one. Okay, so that's kind of there. Okay. Oh, I meant the left over. Sorry, Brad, I didn't. Yeah, I know. I'm not using that on here then. Cheers. Viscous drag. Okay, so this is the next one to note then is drag is the resistance to the flow of a fluid. Okay, so viscous drag is the resistance to the flow of a fluid. Guys, do you mind? Sorry. What I want you guys to think about at this point is we have an object that is free falling essentially through a liquid. A little bit the way you would kind of compare this is like a skydiver jumping out of a plane and it's falling to earth. And what causes that is gravitational pull or weight. Okay, and we have this downward force. Now, viscous drag essentially is the size of this arrow above. So it's the resistance, it's the air resistance, it's the fluid resistance, whatever it is, but we call it viscous drag. Okay. Now, what we need to realize at this point is if we drop back to this animation here, A, B, or C, which one has the most viscous drag? Which one exhibits the most So which A, B, or C, which one has the most viscous drag? Yep, Brad, you're straight in there with C, so you're getting it now. That's good. Do we all agree? So this is going to have a high drag, and in comparison, this one's going to have a low drag. Okay, excellent. So we can relate this straight back to here. Now, what we need to realise, and this again applies. So let's relate this to a skydiver again. I think if any of you studied physics at GCSE level, you probably studied skydiving and the forces behind it. As that object increases in speed, that drag increases to match that speed, if that makes sense. And what you'll find eventually is that an object falling in a liquid, and you can see this here, falls at a constant velocity. So you actually get a terminal velocity in that sense. So the thicker that material, the more viscous that material, the quicker you hit that terminal velocity. What the terminal velocity is, that object is not going to accelerate anymore. It's just traveling at a constant velocity all the way down through. And you can see both B and C have got that terminal velocity exhibited there. But one is obviously higher than the other. Okay, so it's really important to understand then what we mean by viscous drag. And it's the viscous drag that makes the substance viscous in that particular sense. This bit here talks about what happens when an object does speed up. Okay, so as the speed of air passing over the car is increased, the flow pattern changes from laminar to turbulent. So we can actually see this happening here. There's a transition that starts to cause a turbulence. Okay, the changeover from laminar flow to turbulent occurs at a speed known as critical velocity. Okay, so what we tend to find is if you're traveling at a low speed, you can see this here, the air moving over a car remains streamlined or laminar all the way over that, and there is no transition. Now, if this car speeds up, see this here, we can move from laminar to turbulent. Okay, so it's just making sure you understand that. So that's laminar and that's turbulent. Okay, and the speed at which we get that transition is known as the critical velocity. Now, critical velocity is going to be very dependent on the object we're talking about. Now, if we're talking about a really box-shaped vehicle, like a van, like a big boxy van or a lorry, that critical velocity is going to be much, much lower than if we're talking about a Formula One car. Okay, so if your car is really smooth like that, then that air is going to pass over much smoother without going into the turbulence in that sense. Now, turbulent flow causes more drag than laminar flow. That is a really important thing to note down. Okay, so if you are given a situation where you've got turbulent flow on one diagram and laminar flow on the other, and you're talking about which one would cause more drag, then it's the turbulent flow. Turbulent flow into more drag. There we go. Okay, so turbulent flow, more drag, and laminar flow is less drag. Okay, it's just basic aerodynamics. I would say yes. A lot of this is about aerodynamics, and it's getting you thinking about what I would say, guys, to really visualize this is just go back through some of the slides and just look at, for example, like that diagram there. This car has been designed to be streamlined and aerodynamic, and what you can see is that a lot of the air coming off the back of this car at this end is still quite laminar. There is a bit of turbulence in there compared to this side. If you compare this side with this side, what you'll notice is that the air is flapping around a bit more at this end, this back end. But it's very smooth. If you would stick like a lorry or a really big boxy van in a wind tunnel like that, you're going to get a huge amount of turbulence. Now, the way that turbulence tends to manifest is actually shown here. So this is where this is basically laminar to laminar, okay, and this is laminar and then you're getting a little bit of turbulence in there. So there's a bit of turbulence in there, and this is really turbulent. Okay, so this is laminar, so really big turbulence here. And you can see the way that that air is starting to circulate and mix, and it's that turbulence that can cause a problem. The way then I want you to think about this point here, this turbulent flow. This helps if you follow Formula One, if you understand stuff about Formula One. If you've got one car traveling in that direction, and you've got another car traveling behind it, okay, it's possible that this car will cause turbulent air here. So the air coming over this car causes turbulence here, and then this car is going into turbulent air, and that causes drag. Now, there's a sweet point here. Now, if these cars are really close together, it's possible that you can get something called a slipstream. Okay, so at that point, you might want to look up what a slipstream is. Okay, slipstreaming is where resistance can actually completely drop off, and it's almost like you're moving into a vacuum in many respects, and it just reduces that drag almost to almost zero. Okay, but if there's a big distance between those two cars and the car behind hits turbulence, it can increase the drag, and what that can cause is a reduction in the maximum speed that that car can travel at. So do have a look at the slipstream concept, but also consider the impact of. Just going to write that meter so you can see what it is. So look up slipstreams, but also consider the effect of two cars driving right behind each other. Is that what? Yeah, so geese fly in slipstreams, absolutely. And it's that V-shaped pattern that reduces the turbulence that's coming off the next one in front. And if anything, it actually causes this really nice smooth air to travel over those geese. And then the next goose gets that slipstream from that. There's a lot more to that than what I've just explained, okay? But on a really basic level, yes, definitely. Now, this leads us to the last bit. This isn't the complete finish of Unit 5. There's a couple of bits I'm going to do with you guys on Wednesday when you're in, just to finish the topic. But we're going to quickly finish by talking about something called Bemoulli's principle. Now, if you look up Bemoulli's principle on Google, you'll find a really nasty equation. Key thing to note, you do not need to know or use the equation relating to the principle. That's good news because it's horrible, it's really complex, and like I said, there is no maths involved today, it's just understanding principles. Now, Bemoulli's principle helps us to explain how an airplane wing essentially works, okay? Now, here we have a very simple airfoil. So you might see this called an airfoil. If you hear that word airfoil, what it essentially means is one of these. It's a wing, okay? And wings are designed to cause lift, okay? So what makes a plane fly? It's wings, essentially. Obviously, it needs an engine to give it thrust, but it's the wings that give it the lift, that take it off the ground. Now, the way that these are designed, essentially, is to make the air, the laminar air that's coming in, so if I do this in a different color, actually, we're going blue, the air coming in is laminar. Some of it is forced up and over before joining up with the air down here, whereas some of the air is able to just carry on unimpeded. Okay, now the key thing to note here is that when a smooth flowing fluid, i.e. in this case, air is an example of a smoothly flowing fluid, when it gains, so the key thing to note here, sorry, is that on the top side of the wing, pressure drops, but the airspeed picks up, it gets higher, and underneath you get more pressure, but you get slower air, okay? So it's making sure you understand what's going on there, okay? Thinking about why that is. Think about the fact that what's going to happen here is that these streamlines here and here are getting closer together. So when those isobars, remember the isobars, they get closer together on the weather, that's low pressure. And here, the isobars stay far apart, so there's higher pressure. And what this leads to is a high pressure here and a low pressure here. And essentially what this can do is it causes a lift. Okay, it causes that lift in force. And that's essentially what helps the planes, firstly, to take off, and secondly, to stay in the air. So you keep that lift in play. Now, what you need to know, essentially, is written there. Okay, so you need to be comfortable with those two, and you need to be able to relate it to this diagram down here. Okay, so there's a lot to take in there, but that's it. Okay, that's the content today. So what I would suggest you do is just go back to, there were some really key slides. This slide here is taken straight off the revision guide. Go through each of these points and make sure you're comfortable with what each of these points are saying. Okay, tick them off. If you're not sure about one of them, go back through the content. The other one that we need to be comfortable with is this slide here, because this covers the key learning points for the viscosity. So go through each of those points, make sure you're comfortable with what each of those are. And then finally, just make sure you're comfortable with, too many slides there, what we mean by Bernoulli's principle. Okay, so Bernoulli's principle, or the Bernoulli effect, is where it just applies everything we've learned earlier. So where you've got that directional change that leads to a pressure change, and in turn leads to either air speeding up or air slowing down. Okay, and we're relating that to an airfoil, and that gives us the lift. It's just really applying everything we've learned already. Now, just to finish, that's me.